Oops, sorry. All right. So after these exciting events that the Jürgen Fest is on fire, we can continue with the next talk in the list. The next invited speaker is Dr. Peter Cooper. He got his degree from Rutgers and a PhD at the University of Yale. He loves sailing, and currently he's an emeritus professor at the National Laboratory at Fermilab in Illinois, where he collaborated with many experiments of particle physics. He's a distinguished member of the American Physical Society, and we're very happy that he agreed to participate in the event. So, Dr. Cooper, the microphone is all yours.
Thank you. Let me see if I can share my screen here. Yeah, that'll work. All right. Are my slides up?
Yes, we can see them.
Okay, so back. Hello. My slides may be up, but I can't. Oh, great. They're oh, beautiful. Stop that. Let me go back to the beginning. All right. So congratulations, Jürgen. Happy birthday.
Thank you, Peter.
I decided to focus this on the Richmeister and go through your rich history, because it seemed like I was the one to do that, because we've heard significant amount, we've heard from Stefan about W89, we've heard from Augusto about NE62, you're going to hear from me about CellX and CKM. So let's get started. But I can't seem to move my slides, which is not good.
We can see them.
I know, but I got to be able to advance them. Oh, there we go. Except this is on auto advance, and that's not going to work. Here we go. Fine. Okay. So first, for Jürgen's history with respect to at least Fermilab and such. So Jürgen, after his thesis on W89 and a couple more years, right? He came to Fermilab in '93 as a postdoc to bring, what he knew about riches and charm baryons from W89 to CellX, which was E781, because we were in the process of designing and building a fairly good size phototube bridge. He and I shared an office for most of his, Jürgen, you were there, what, 5 or 6 years, something like that. And we shared an office for almost all of that, which was interesting and exciting. We cleared the 10th floor several times, and neither of us is very quiet. And we've been working together ever since on CellX, on CKM, on NE62, and whatever comes next. So this is 28 years now. So I'm going to focus on his contributions to the rich world, but he did a whole lot of other stuff too, which is required to at least mention. So, little things like he and I wrote the offline software. He did all the data acquisition hardware and software. Later on, he did several CellX analyses with his students, some of whom are going to talk later, so I'm not going to talk anymore about their theses, they are. And more stuff that I don't remember. All right. One needs to go through riches a little bit, though we've heard some of this from Stefan and a little bit from Augusto. These are fundamentally very simple detectors. It's a can of gas with a mirror at one end and a photodetector at the other. And as prior to ring imaging counters, which, as I guess Stefan observed, the first real instance to try and do that was the Omega Rich. Its only problem was it didn't work. Before that, what everybody used were threshold Cherenkov counters, which was a can of gas with a mirror and one phototube that if it fired, says a particle was high enough to be over Cherenkov threshold for whatever the radiator was, typically whatever gas was in that can. And that made in multi-particle environments, that was real hard. You had 4 particles going through that can and one of them gave light, or at least one of them gave light, and you didn't learn a whole lot. That's what drove the application of rich technology seriously. The basic Cherenkov physics is you put a position sensitive photodetector in the focal plane of that mirror, and being in the focal plane, if you do the optics, you've interchanged the role of position and angle. So the position coordinates in the focal plane are the angles of the particle that makes the light, and the light is focused to a ring. The radius of that ring depends on the relative velocity of the particle compared to the velocity of light in the medium, and it has to be higher to get Cherenkov light, so there's a threshold. And the center of that ring gives you the angles of the track. So that little cartoon down on the right with the 5 circles, that's one event out of the cell X rich. The 3 tracks on the right, the red one and the 2 green ones, are a kaon and 2 pions. And the track on the left are probably 2 other pions, 2 negative pions. And you notice the one that's colored red is red because its radius, if you look carefully, is a little bit smaller than the green one just above it, which means that it's slower, above Cherenkov threshold, but still slower than what an electron of beta equal 1 particle would be. And that one is uniquely identified as a kaon. We'll get back to this picture later. But the centers of those particles measure angles, and the radius measures the velocity, right, relative to the velocity of light in the medium. So that's a vector. It's a vector velocity spectrometer. You get 3 numbers for each track, and you get them sorted out. You know which of those hits go with which tracks. So you don't have the problem anymore of, oh, the Cherenkov counter fired, but which track did it? Another nice thing, which we never exploited much in CellX, but we certainly do in Na62, is that Cherenkov light is isochronous. It all gets emitted at the same time, right? The Cherenkov light going down the wavefront and the particle going at the speed of light all go at the same rate. That means all the light from a given particle gets to the phototubes or the photodetector at the same time. So for example, in Na62, we have a time resolution on each track, of which is usually only 1, of order 100 picoseconds, maybe a little better. At that level, it's hard to measure. You got to ask what you compare it to. And because there's individual rings and you can do pattern recognition, this single event display, each one of these little dots, as you see them, is 1 phototube. And you can decide which phototubes go on which rings and sort this all out and know the time of the track, as well as, fitting it. So you, in fact, get a 4 vector out of this thing, a 3 velocity plus a time. In fact, our first signal event in Na62 had another ring in the rich, but it was 60 nanoseconds at a time, and we knew it was 60 nanoseconds at a time, so it had nothing to do with the rest of the event. All right, I still can't move this worth a darn. What is going on here? I'm having trouble moving my slides, advancing them, I should
Up
say.
and down arrow.
Yeah, that's what I was doing.
Okay.
Right. Unfortunately, well, I know how to fix this, but all right. So what does Jürgen have to have done with riches? You've heard some of this already. So his thesis, included the W89 rich, and we heard that from Stefan. He then came to Fermilab, and we built and ran, we designed, constructed, commissioned and ran the CellX Rich at Fermilab. We then went off to design 2 riches for CKM, one for the Kaon and one for the Pion. As you'll see in a minute, CKM is the predecessor to NA62 to try and do the same decay mode, K plus to pi plus nu bar. And it used 2 velocity spectrometers, one for the Kaon, one for the Pion. And NA62 is morally equivalent. So we then designed, Jürgen and I, mostly Jürgen, the rich for the NA62 based on the CellX rich. And that's the beast that's in there now. And I'll talk about that in a few slides. And then since nearly the beginning, there's been the international workshop on ring imaging Cherenkov counters since the early 90s. I can't remember when the first meeting was. And Jürgen has been in those things since the beginning and has been on the organizing committee, as best I can tell, forever. I still can't. We're going to do this the old-fashioned way because it'll work. Right. Okay, so I had to put this slide in because I didn't know whether I was going to talk before or after Stefan. So this is a 1-slide summary of what Stefan told us. There was the Omega Rich from the mid 80s, even before, I think. Omega was a multi-particle spectrometer at CERN that ultimately got adapted by W89 for Jürgen's thesis experiment and all the others they did. And they were doing this in a hyperon beam, and they were looking for charm particles. They, in fact, discovered what now we call the lambda C, what they called the A+. They built a new photodetector, one that worked, that was terrible in its, you know, it was a very finicky beast. It was full of this gas called TAMI, which among other things smelled terribly and ate everything. It was corrosive, but it did work. Alrighty. At a similar time, my colleagues and I were trying to plan what to do for our next hyperon experiment for the late 80s and early 90s. And we wanted to go after the same kind of charm physics that W89 was already pioneering because they were a few years ahead of us. And therefore we needed a multi-particle spectrometer, and therefore we needed particle identification, and therefore we needed Cherenkov counters. So I designed a rich using phototubes instead of CAMI gas detectors, because we had heard many bad things about those and we knew they were hard, and phototubes were dumb and stupid and worked. So you're not going to be able to read this note, but that's my design note from November of '84, called an A+ rich counter. And the idea was, you know, take out that half a square meter of TAMI drift chamber and put in a half a square meter or a square meter, or in fact 2 square meters is what we ended up doing, of phototube array. The children here now, of course, are merely the professors with their own students, might notice that there was a time when notes actually got written by hand with a pencil. So that was the idea. In the early 90s, a half a dozen of us built a prototype for this kind of phototube rich. The phototube you see there is an R760. It's a Hamamatsu phototube. It's got a quartz window. It's the size of one of your fingers. It's a 1/2-inch phototube, 12 millimeters. And it's fast, and it has quantum efficiency down to 180 nanometers, which is, you know, quite good for what the Cherenkov optical spectrum looks like. As I said before, in '93, Jürgen came over from CERN with his, you know, his first big project was to join the rich team and make all that happen. The picture below is the CellX rich installed. It's 10 meters long. It has 2,000 phototubes. 400 or 500 of which are these Japanese tubes. The rest were Russian equivalent tubes because they were a whole lot cheaper. And 2,000 phototubes from Hamamatsu is not a small budget item. It had an atmosphere of neon, which turned out to be basically the perfect radiator. Neon is a little pricey, but otherwise it was an atmosphere, which meant you didn't need a vacuum system, you didn't need a pressure system, you didn't need a temperature control system. You just closed the valve and the number of electrons inside the can stayed the same, so the Cherenkov angle stayed the same. And if the temperature went up and the pressure went up, we didn't care. The number of electrons was the same, and it's the electron density that determines the Cherenkov threshold. This was in a 600 JeV sigma minus beam, hyperon beam. And for scale, it had about a 15 JeV pion threshold, about a 40 JeV kaon threshold, and about a 75 JeV proton threshold, which means everything above those, for a factor of 2 or 3 or 4, we could tell the various particles apart. We would have particle ID. You'll see that on the next plot. This picture you've already seen. This is Jürgen aligning the mirrors, which after what I always remember this picture every time I remember what our colleagues did trying to align the mirrors for the Na62 rich. Never mind. So here's that event. And it illustrates some of the features of the detector. So look at that red circle. It's red, so you can tell who it is. That's track 5. That's 108 JeV negative particle that is unambiguously a kaon. That's the only ring radius for 108 GeV over C momentum. That's the only particle assignment that's consistent with that circle. The 2 other green circles, one just above it, the one to its right, those are identified as pions, but I got to look and see who's who here. They're kind of ambiguous. You know, they're very likely pions, but they're almost as likely to be muons or electrons. That is, the ring is as big as it's going to get, and you can't tell them apart. But they're definitely not protons, for example. Likewise, this blue one over here on the left, this negative track, that's actually identified as a muon, but it's, you know, if the muon, you know, the relative probability of it being a pion to a muon is 90%. So it's ambiguous, you can't tell. This is sort of typical of what rich data looks like. Nonetheless, this is a 5-track event, and we've got it all nicely sorted out. And we have angle measurements for the from the centers of the individual rings that we can match up with the tracks and know which track is which from the tracking system in the magnetic spectrometer. All right, so to give you a flavor, this was one of our unbiased propaganda plots. This, I think, we just took on a beam trigger and then took everything that we got, right? Now, there was a % or 2 of interaction length in the beam. We had targets. It was a charm production experiment. But you see every species you can imagine on the top plot. So what we're plotting here is the momentum of the track as measured by the magnetic spectrometer and the ring radius in centimeters vertically. So you can see on the top plot, there's all the way up at maximum ring radius are electrons, because those are essentially infinite velocity for any momentum we could measure. So their ring radius is always the maximum. Next below that, as you go, the first set of curves going up are pi's and mu's, and you have to look on a better plot than this to tell them apart. But while they're rising, you can tell them apart. It's just there's a very large number of pi minuses in a negative beam. The next one is kaons. The next one is antiprotons, sigma minus, cascade minus, and omega minus. And then in the bottom plot is exactly the same for the positive particles. So that last curve there at starting at the 150 JeV at the highest momentum, those are anti-omega plus. This thing clearly works. Right. The first I have to apologize for the picture. That's my copy of the front page of Physical Review Letters where we published this. And it got wet, but I can't get into my office to get the original. So you got what you got. The most important result out of CELEX was the discovery of a doubly charmed baryon, cascades of C++, which is 2 charmed quarks and an up quark. We saw that in 2 different decay modes. And that picture on the PRL is the single event display of the longest lived and nicest looking of those candidates, of which we had, I don't know, a dozen or something. I can't remember anymore. But each one of those blue tracks has a particle ID associated with it. That's because that's what the Rich said the particle was. And what's in here is a proton, 2 kaons, and 2 pions. So particle ID kind of mattered. Without that, the combinatoric background would have been hopeless. We then looked also in the, what was it, proton D meson K final state, and saw it there too at the same mass. LHCb more recently has their own candidate for the singly charged one and the doubly charged one. And they claim they're inconsistent, and theirs has a lifetime of several hundred femtoseconds, and our lifetimes were less than 33 femtoseconds. So whatever we're seeing, they're not the same thing. Don't know what to do with that. I went and I looked to see what Jürgen's hot publications were. And not surprisingly, the 3 top publications were the 2 doubly charmed baryons and the hardware paper for the Na62. Alrighty. While we were doing, we took data in CELEX from 95 to 97, if I recall correctly. And while we were doing that, we were thinking about other things. I had thinking about this particular other thing since 92. And those thoughts turned into a proposal at Fermilab called CKM for charged kaons at the main injector, which was, you know, the predecessor to Na62. Same experiment, same physics goals, different accelerator, technically different in some important ways, very similar in many ways. We proposed that in 98. It was approved in like 2000-ish, 2001, I can't remember. And it was then killed by the P5 committee, the Particle Physics Project Prioritization Panel. I will have more to say about them later. But the upshot was, you know, we took these ideas, some of these ideas to CERN, and you'll see in the next few slides how that went, which was very well. The idea of CKM, I mean, as Augusto told us quite nicely before, you know, if you want to measure a 10 to the minus 10 branching ratio with 10 to 1 signal to noise, you need 11 orders of magnitude of background rejection against all the other decays. And at that level, you have to be very careful about everything you can imagine that can go wrong will go wrong. And all the things you can't imagine will go wrong too. So you have to have redundancy, measure the same thing several different ways in order to be able to pry apart this weird thing where this pion scattered somewhere, or where this, you know, K0 decayed into a mu, or God knows what else is confusing you. And the way CKM was going to do that was to have both conventional magnetic spectrometers, measure momentum for the kaon and for the pion. Remember, this is pi plus, K plus goes to pi plus nu bar. So a charged kaon goes to a charged pion and nothing else. You got 2 tracks to measure. And we were then going to do exactly the same with 2 rich detectors as velocity spectrometers, independent measurements of all the kinematic quantities, and then compare them, because they're very different detectors. They have very different systematics. They're subject to different problems, and you can use one to lever against the other. And you can see Jürgen and Antonio were on that proposal. which was approved and then disapproved. So the way we cast that systematics problem was non-Gaussian tails. That is, in any distribution for anything you were measuring, but most importantly, the missing mass recoiling against the pi plus, each process which contributed to that had a frequency, right, which usually was very small, except for the real one, and had a different distribution function for what the mass resolution function was, and may or may not have actually even been Gaussian, depending on how baroque the process was that was actually causing it. So to make this point, we kept preaching this to all the committees before we got approved. Augusto was on one of those committees. Jürgen came up with the CKM Gaussian distribution, which I don't have a copy of. Jürgen, if you have a copy of it, send it to me. It's 7 different pictures or portraits of Carl Friedrich Gauss, right? All the same guy, but all different. He also did, as part of the proposal, did a simulation of k pi 2. That's a k plus decaying into a pi plus, a pi 0, and a pi 0, and nothing else. And then measure the missing mass of the pi 0. And this plot on the upper right is the result of that simulation. 10 million Jeon events was a fair computing job in those days. And what's plotted horizontally is reconstructing the missing mass of the pi 0 squared using just the momenta, and vertically using just the velocities from the ridge. And you can see, you know, what's not surprisingly a nice, pretty Gaussian by Gaussian, you know, 2-dimensional Gaussian distribution. And you can see that the velocity resolution is, you know, something twice of the momentum resolution, no surprise, but they are completely independent. Now, the bottom plot on this page is data from NA62, same plot. In this case, there's no kaon rich, but it's using the pion rich for the pion. And the scales are much bigger, and you can see there's all sorts of features in this thing. There's a huge spike in the middle. This plot has roughly 10 times the area of the one above it. And in fact, the 2 red square boxes are the 2 signal regions for NA62. These are events that are tagged as pi zeros, that is, we saw photons in the photon detector. So these are definitely not signal, but you can see this dribble of events running diagonally across the upper box, and those should terrify you, because those are candidates for background. You know, if your photon detectors are inefficient for those events, you're going to want to call those pi nu nu bar candidates. All right. So wasn't September, now that Augusto reminds me, we were at CERN, Jürgen and I, just before September. I think we were there in July or August, I can't remember, to pitch this idea for putting a pion rich into P326, which was the proposal that became NA62 when it was approved. And of course, before we showed it to the PAC, we had to show it to the collaboration. We did that. And it was well enough received, clearly, that they put it into the proposal. An interesting moment was had when Jack Steinberger was a member of the collaboration. Came to all the meetings till recently. Of course, he just passed away. And I only knew Jack, you know, by reputation. I was introduced to him, but I didn't know him. I don't think Jürgen knew him either. And after our presentation to the collaboration, he asked us to come to his office later because he had a few questions. As Jürgen would say, oh, shit. We thought we were in trouble. We weren't. Jack was just fine. It was okay. He just had questions. It's one of the ways I got to know Jack. We didn't get, so ultimately it was proposed, it was approved, it was, the Rich was part of NA62. It's in the experiment now. But neither Jürgen nor I got to participate in any of that for 5 or 6 or 7 or 8 years because we couldn't raise any Mexican or American funds to do it. So it was built with euros. It was built in Italy by some of our collaborators. And we got to be in working groups in Kibbutz a little bit. It doesn't work as well as Jürgen Selleck's Rich. The photon yield is 60 or 70% of what you would have extrapolated. But it works well enough to do the physics, and that's all that matters. So there it is, that big green can. It's 17 meters long. It's got to be 2.5 meters in diameter, something like that. And it has 2 phototube arrays at the downstream end. You're looking upstream in this picture. So at the end that's covered by the calorimeter where you can't see it. And its mirrors are split so that the left mirrors, bend the beam, point to the left and go into the left phototube array. The right mirrors bend to the right, point into the right phototube array. That's necessary because you don't want to touch our 1 gigahertz beam. That's a good thing to keep your fingers out of. You get burned. And in fact, there's a pipe down the middle of this thing for the unscattered, undecayed beam, or it would light it up like a Christmas tree. So you saw most of this from Augusto, but again, I didn't know Augusto was going to speak before I did. So the 1-page summary of NA62 is in 2016 through 2018, we took 3 years worth of data, got a total in the 3 years, as Augusto showed, 1 event in 16, 2 events, in 1 candidate in 16, 2 candidates in 17, and 17 candidates in 18. And the total expected background for that ensemble is 7. So that's a not quite 4 sigma observation, which you can call a discovery or not, as you will. The Rich played exactly the role it was designed to play to do this physics. Could it have been a little better? Yes. Was that terribly important? Probably not. And as I say here, Augusto already told you the rest of this story. But the preprint on the right, which went up on the archive on the 27th of March, kind of 6 weeks ago, is the report of that. Now, in all fairness, we proposed an experiment to do 100 events, right? Not 13. So we have more work to do, and we're going to continue running, as Augusto told you. There's the Rich workshops, which have been going on since the 90s, and which Jürgen has been on the organizing committee on forever. And this is a fun crowd of people. The poster is the poster for the one that Jürgen ran in 2004 in Playa del Carmen, which was the prototype for the NA62 meeting we had at the same place in Playa del Carmen, a year ago. And if you look carefully, there's a single event display superimposed on that Mayan frieze. And that's one of I think that's the same candidate that's on the cover of PRL. No, it only has 4 tracks. It's a different one. So Jürgen has been involved in these things forever. The last one was in Moscow in 2018. I didn't go. I don't know. The next one was supposed to have been this year. I assume that didn't happen. And, he's one of the leaders in the Rich world and will continue to be so. All right, now my rant on P5. When all is said and done, the Rich detector is a detector. It's real good. You have to have it. But the object of the exercise is to do physics, and that's a tool to do it. And It's the physics that matters and not the individual detectors. You need all the detectors. They all have to work. They have to work right. You need a good plan, but it's the physics that's the goal. So Jürgen and I have been working together since '93. We've been pretty much doing the same physics. We've been on all the same experiments together, almost all. I wandered off into, done some dark matter things, looking for dark matter with bubble chambers. But other than that, at least in terms of classical particle physics, we've worked closely together since then. NA62, once we moved CKM's ideas over to CERN, took Jürgen back to his roots at CERN, took me to CERN for the first time. That's been very pleasant. And then I observe after, 15 years of history now, that CERN has this broad and vibrant particle physics program spanning everything from anti-hydrogen to the LHC and all sorts of stuff in between. Fermilab has some neutrino experiments and a couple muon experiments, and SLAC, the home of the linear collider, has the Vera Rubin telescope. So our friends who brought us the P5 committee should be proud of their nuking the American particle physics program, because that's what they did. As far as Jürgen and I are concerned, we're not unhappy. We're doing what we want to do. We're just doing it at CERN. So to summarize, Jürgen is and will from some quite time and will continue to be for some time, hyperactive, overenthusiastic, and neither shy nor quiet. The breadth and depth of his technical skills, the amount of stuff he knows how to do and does and make work is impressive. In addition to the riches, there's the physics, there's software, both online and offware, there's computing farms of all descriptions, there's data acquisition, there's even more stuff. There's even herding Italians, which is my description for his running the data quality group at NA62. And this is because I love my Italian colleagues, but they need some organization, and Jürgen's good at that. He has one of the lowest thresholds for bullshit of any physicist I know. And you're going to hear about it if you try and BS him. Don't do that. I would have loved to have put more pictures in this thing, but they're all locked in my office and I can't get into my office, so I apologize. So Jürgen, happy birthday, Mazel Tov. We've got more beer and mezcal to drink. We've got more physics to do. Thank you.
Thank you, Peter. Very nice. Very remembering things. Very nice.
Fragen?
Yes. Questions. The next Rich workshop will be in Edinburgh. It was planned for this year, but it was moved to next for known reasons. Yeah.
Yes, for known reasons, indeed.
And I also didn't get to Moscow because they didn't issue us the visas on time. Yes. Russian bureaucracy, yeah?
Yeah, right.
Peter, thank you very much for this nice talk. The memories are amazing. Thank you very much.
So, as you might have noticed, we are back. Limon fixed the server and replaced it by a spare one, yeah?
You will buy Limon a beer.
Yes. We will have that tomorrow at my place, yeah? So you're all welcome for the party tomorrow.
So I don't have access to the YouTube, I believe, to see if there is any questions there, but there may be some questions or comments. This excellent talk. Thank you.
Yeah, we have to ask Nora because I'm also not on YouTube.
No. The talk will be uploaded to you in YouTube, I think in an hour, more or less, because due to the falling, we'll lose all the connections.
So it's not on YouTube. Okay, there's no YouTube for that talk, but it will be later. Okay, there's still Stefan. There's Ibrahim Torres connected, who was my first student in physics here.
Hi, Jürgen. Hi, Peter.
Thank you.
I will show you a picture of both of you later.
Yeah, okay.
I was afraid of that.
When everyone were young.
Yeah, I think we're a little bit short of anecdotes of Jürgen, but those probably will come up later on.
Please, to everybody, if you can connect to the afternoon talks, I know for people living in Europe is a difficult thing, but please connect. You will be very welcome, and we'll be very happy to have you all connected.
Thank you.
Okay, so very nice, Peter, for remembering all this, all the stuff we did together. Yeah? We shared office 5 years.
Yep.
In CERN, and then at Fermilab, and did some work on Celex there. Yeah?
The 10th floor a few times.
Yes.
So in terms of time collaborating, you two are the ones that are the longest in time of collaborating?
I think so.
Yes, we started something like 92 when we met the first time, 93. So it's a few years, yeah, nearly 30.
Well, we clearly have similar tastes and similar strengths. So what's wrong with that?
Yeah. And we introduced Peter to Mezcal.
Uh-huh.
Ah.
Irene to Mezcal. Anything possible after that. Irene's my wife.
Yeah, because the last 2 years where we took data in 17, 18, when we were at CERN, Peter stayed at our place to when he came to NA62 for the shifts. So
And you took your mezcal all the way there?
Yeah, so we had some mezcal, and we had our deliveries. Yeah, every Mexican who came to CERN to visit had to bring a bottle of mezcal with him, so we could continue. Yeah. Not all complied, Gerardo. Yeah.
Actually, we still have 2 bottles of mezcal in the office at CERN.
Yes.
It's good to have inventory. There's a little
Yes.
import.
Yes, we are still equipped. Obviously, there's no alcohol allowed during on CERN side, obviously, yeah, but
Yes.
during working hours, yeah.
Right.
But okay.
Never mind.
Yes. And Peter was here in the institute several times, yeah, as well.
Yep.
Yeah.
That was what I was going to ask.
He was there for my defense. He was my
there, yes.
external advisor.
Yes, he was there for the defense of Ibrahim.
Yeah.
We did
What
some
year was
other
that?
things. What year?
Must have made,
2006.
2006.
I made several
Yes.
trips for San Luis while we were still
Yes.
analyzing data.
When was the last one?
Oh, I don't remember.
It wasn't too long ago, because he came to visit Eric for a meeting of the bubble chamber, no?
Yes, that's right. And then I came to San Luis. Yeah,
And so we brought him also to San Luis.
yeah, and Eric got me sick.
Yes.
And not only you, 90% of the PICO collaboration.
No, I wasn't. I was the one Jürgen had to deal with.
Yeah, was 2016 that
2016,
when we had the PICO meeting.
Right.
Yeah.
But I learned, and I lowered that number when the deep collaboration meeting was here. It came to roughly 10% of people got sick during the deep.
Well, that's better.
Oh, okay.
Yeah, much better.
Yes.
When we had
It's
the
good when-
Celex meeting here, nobody got sick, I think. Not that I
Oh.
remember.
I don't-
So the food in San Luis Potosí is better than in Mexico City.
No, I don't think so. Sorry.
You don't think so?
No, that's
Another
because you
chilango, yeah.
Jürgen, that's because you didn't give them Mexican food. I mean, it's impossible that 0% get sick with Mexican food if they are foreigners. At least 5 to 10. Yeah, 5 to 10% is acceptable. 90 with pico. I blame that at the night before, one of the nights I took them for mezcal.
Okay.
It was also the food.
So let's see, this is Mexican vaccine, mezcal.
Yes.
No, absolutely not. It's medicine, but not vaccination more so.
Right.
But there are people who claim when they drink mezcal, they don't get COVID.
Okay. There are
Yeah,
people
so-
who claim all sorts of things.
Okay.
Okay, it's almost time to leave. Thank you very much,
Can cut
Eduardo.
the transmission. Okay, I'll stop the